Let's talk about the central limit theorem. If random samples of size n are taken from a population with mean mu and variance sigma squared, then the distribution of the sample mean x bar approaches a normal distribution with mean mu and variance sigma squared over square root n as n approaches infinity. The standard deviation of x bar is sigma over square root n, which makes sense because if the variance is sigma squared over n, then the standard deviation is going to be the square root of that, which is sigma over square root n. This is called the standard error, or SE. In this case, it is the standard error of the mean, or the standard error of the sampling distribution. This is the key fact I want you to remember. So sigma x bar, the standard deviation of x bar, is the standard deviation of x divided by the square root of n. So this central limit theorem is one of the most important theorems in statistics, and it's quite a mouthful, but for now, I just want you to remember what I've circled in red there. Now, the shape of the distribution of the sample mean x bar is approximately normal if the population itself is approximately normal. In other words, it doesn't matter how big the sample is. If the population is distributed normally, then the sample mean is going to be distributed normally. Or if the size of the sample n is greater than or equal to 30. So unless the population is really skewed, if you have a sample of size 30 or more, then that sample mean is going to be more or less normally distributed. For example, in the United States, the heights of adult men are approximately normally distributed with mean 69 inches and standard deviation 2.8 inches. Find the probability that the height x of a randomly chosen adult American male is between 68 and 70 inches. We've seen how to do this. We can do this on the TI, TI-83, TI-84, TI Inspire. Normal CDF, this is our lower limit, 68. Okay, this is our upper limit, 70. This is the mean, 69, and this is our standard deviation, 2.8. So that's 0.2790. That's the probability that a randomly chosen guy in the United States is between 68 and 70 inches tall. Okay, now we take a random sample of 25 American men and measure their height x. Find the probability that the sample mean, x bar, is between 68 and 70 inches. Here we're going to refer to the central limit theorem. The standard deviation of x bar is the standard deviation of x divided by the square root of n. So by the central limit theorem, the mean of a sample of size 25 is approximately normally distributed with mean 69 inches. Notice that the mean of the sample means, that's going to be the same as just the regular mean, the mean of x. So the mean of x bar is the same as mean of x. And the standard deviation of x bar, that's going to be sigma over square root n. In other words, it's the standard deviation of x, 2.8, divided by the square root of the sample size, so square root of 25. So again, by the central limit theorem, we can calculate this using normal CDF on the calculator. Here are upper and lower bounds, the mean, 69, and then we would just enter this on our TI, 2.8 / square root 25, and that yields 0.9258. So if you have a sample of size 25, that's the probability that the sample mean of those 25 guys is going to be between 68 and 70 inches tall. Okay, now let's take a random sample of 100 American men and measure their height x. Find the probability that the sample mean x bar is between 68 and 70 inches. Same story by the central limit theorem. The mean of a sample of size 100 is approximately normally distributed with mean 69 inches and standard deviation 2.8 divided by square root of 100 inches. So we would enter normal CDF, 68, 70, 69, just as before, except this time the standard deviation of x bar is 2.8 divided by the square root of 100, and that yields 0.9996. So if you have a sample of size 100, you're almost guaranteed that the average, that the sample mean you get from that sample is going to be between 68 and 70 inches tall. Now, why is this? The sample mean x bar has a standard deviation of sigma over square root n. The larger the n, in other words, the larger the sample size, the smaller the standard deviation, because the n is in the denominator. Again, the heights x of American men, adult American men, are approximately normally distributed with mean 69 inches and standard deviation 2.8. Here's what the distribution of x looks like. So this is a normal distribution with mean 69 and standard deviation 2.8. For a sample of men's heights of size 25, the sample mean x bar is approximately normally distributed with mean 69 and standard deviation 2.8 divided by square root of 25, which is 0.56 inches. Here's what the distribution of x bar looks like. Okay, that's for a sample of size 25. And for a sample of size 100, the sample mean x bar is approximately normally distributed with mean 69 inches and standard deviation 2.8 divided by square root of 100. In other words, 0.28 inches. Here's what the distribution of x bar looks like. So notice it's much tighter, much narrower. That's because the standard deviation is much smaller since we have a large sample size. Let's put the three of these together. So if you randomly choose an American guy, the probability that he's between 68 and 70 inches tall is 0.2790, okay, because the distribution of heights looks like this. If you take a group of 25 American guys, the probability that the sample mean will be between 68 and 70 is much larger. It's 0.9258. In other words, there's a 93% chance that the sample mean will be between 68 and 70 because the distribution of sample means is much tighter. It's much narrower than the distribution of heights. And if you have a sample of size 100, the probability that the sample mean will be between 68 and 70 is 0.9996 because it has a much, much smaller standard deviation. And that's why if we want to estimate a population parameter like the average height of men nationwide, we would take a large sample. Because if you get a large sample, you're almost guaranteed that that sample mean is going to be really close to the population mean. This is an aspect of the central limit theorem that I haven't highlighted, but it's important too. The distribution of the sample mean x bar approaches a normal distribution as n approaches infinity, regardless of how x is originally distributed. This is a really cool result. It doesn't matter how skewed x looks like or what x looks like. X bar is eventually going to have a distribution that looks like this normal distribution as the sample size n approaches infinity. That is a cool result.